Hello everyone, I am Miss Hu, your physics teacher. In this video, we will be going through the concept of wave reflection, where we will learn about the law of reflection, the behavior of waves during reflection, how to draw reflected waves, as well as the applications of wave reflection. So, first of all, let us begin with the law of reflection. The law of reflection states that the angle of incidence is equal to the angle of reflection. This is provided that the incident waves, normal line, and reflected waves are on the same plane to be able to measure the angle of incidence and angle of reflection. By the way, here's a meme to brighten up your day. So let's go into a little bit more detail about the law of reflection. On this slide, we're going to use light reflection first to understand reflection. If you have already learned about light reflection, then the law of reflection is not new to you. Understanding law of reflection is very easy once you observe how light reflection occurs. So the diagram on this slide here is showing us light reflection. This is a plane mirror. This is the incident ray that is reflected off the mirror, and this is the reflected ray. The incident angle, also known as the angle of incidence, is measured between the incident ray and the normal line, while the reflected angle, also known as the angle of reflection, is measured between the reflected ray and the normal line. The normal line, also very commonly just called the normal, is an imaginary line that is perpendicular to the mirror, measured at the point where the light ray touches the mirror. So remember that when it comes to waves, we measure the angles between the wave or the ray and the normal, and not from the ray or the wave to the mirror. So this should make sense, because whenever you shine a light ray to the mirror, it reflects in such a way that the angles on both sides of the normal are equal. And that's what we mean by the law of reflection, stating that the incident angle is equal to the reflected angle. Now you will see that all waves undergo the same behavior when it comes to reflection, whether they're water waves, sound waves, or electromagnetic waves. This diagram is showing us general wave reflection. So in this diagram, the waves are shown with these lines, which are the wave fronts. So remember that light rays also have wave fronts like these. It's just that we cannot see the individual wave fronts because they're too close together. So when they're all put close together, we just see a single light ray. But if we could zoom into the light ray, we will see the individual wave fronts just like in this diagram. So to help you understand this diagram better, let's think of this diagram as a diagram that's representing water waves. So each of these red lines are representing the wave fronts of the water waves. So the water waves are traveling towards a barrier, and they will be reflected off the barrier. So the waves that are coming from the source are known as incident waves, while the waves that are reflected off the barrier are known as reflected waves. Now when we measure the angle of incidence, we measure not from the wavefront, but from the direction of travel of the waves to the normal. Now remember that the wavefronts are perpendicular to the direction of travel. So as you can see from this diagram here, we measure the incident angle from the direction of the incident waves to the normal, and the reflected angle is measured between the direction of the reflected waves to the normal. So if we were to backtrack and compare this against the light reflection, this is actually exactly the same thing. It's just that, like I mentioned earlier, all the wavefronts are so close together, they form a single incident ray. But as you can see, this incident ray is also kind of showing us the direction of travel of the light ray. So the incident ray is reflected off the mirror in such a way that the incident angle and reflected angles are equal. And the same thing can also be observed on this diagram. So the incident angle is equal to the reflected angle. So regardless of whatever type of wave it is, whether they're light waves, sound waves, electromagnetic waves, water waves, all waves that undergo reflection will obey the law of reflection. Now, let's observe an animation on wave reflection. This is showing us plane waves that are reflecting off a plane barrier. As you can see, the incident waves and reflected waves are traveling in such a way that they will move in opposite directions, but they're traveling at the same speed before and after reflection, and also the wavelengths are equal before and after reflection. Now let's observe what the waves would look like if they were to be reflecting at an angle. So this animation shows us clearly why and how the waves are changing direction. And they're reflecting in such a way that the incident angle is equal to the reflected angle. Just like with the previous animation, the waves before and after reflection are traveling at the same speed, and therefore they have the same wavelength. Now, based on the animations we have just observed, you should be able to now see which properties undergo a change. So as we saw earlier, the wavelength did not change. Frequency cannot be observed on the animation, but you should know that frequency does not change. Generally, just to help you understand, the reason why frequency of waves do not change when they undergo reflection is because frequency is actually the identity of the wave. Frequency is actually determined by the source. So for example, for a water wave, the frequency of a water wave will be equal to the frequency of the motor that creates a water wave, say in a ripple tank. Once the wave has been generated, it will have that frequency throughout the remainder of its life. So that's what I mean when I say it is the identity of the wave. So just because a wave undergoes reflection doesn't mean that the frequency would change. Remember, that frequency is the number of complete oscillations of the wave in 1 second. So if it's oscillating at a particular frequency, when it reflects, it's just going to change direction. It's not going to change its frequency. Now, for speed. Now, a lot of students always assume that waves will slow down when they undergo reflection. But as we saw in the animation just now, the speed does not change. So the reason why a lot of students always think that the speed would change is because when they look at objects in real life, for example, a ball that bounces off the wall, they're like, oh, it's lost energy, so it will reduce speed. For now, you have to understand that waves and particles don't exactly follow the same behavior. Now, it is a little bit more complex than that. Let's not go into wave-particle duality of light. That's not something that I want to cover in this video, so we'll just keep it simple. For now, just think that waves and particles do not have the exact same behavior. So for now, just think of it as the waves are carrying energy, and when they reflect off the barrier, they will lose energy, but the energy loss is not observed in the change in speed. Rather, the energy loss is observed in the change in amplitude, where the amplitude will decrease. Now, if you can remember what you have learned about the fundamentals of waves, you should remember that the amplitude of a wave is indicative of how much energy the wave particle carries. So if a wave were to bounce off a barrier, yes, it does lose energy, and the energy loss is shown in the decrease in amplitude. So a clear example of how we can see this in real life is that when sound reflects off a barrier, it creates an echo. And echoes are always softer than the original sound. So remember that for sound, amplitude is loudness. So when the amplitude of sound decreases, it is softer. In terms of light, the amplitude represents the brightness. Light rays that are reflected off a surface, whether a mirror or other surfaces, will always be less bright than the original light ray, meaning the amplitude of the light wave has decreased. So this should help you understand what's going on with the waves that undergo reflection. Now, let's look at how to complete a wave reflection diagram. So this is an example of a diagram which we will need to complete. In this diagram, this is the reflector and these are the incident waves, meaning these are the wavefronts. Now, normally, the diagram that's given to you should also indicate the direction in which the waves are traveling. But let's say they don't. And all they informed you was that the incident waves are traveling towards the reflector. So if you are not given the directional arrow, you would need to draw the directional arrow. If the directional arrow is not given to you, the first thing you need to do is to draw the directional arrow for the incident waves. So how to draw it? You need to draw a line that is perpendicular to the wavefronts. Because if you can remember what you've learned about wavefronts, the wavefronts are always perpendicular to the direction of travel. So in my diagram, I've drawn the direction here with dotted lines. In your diagram, you don't need to, but I'm just drawing them as dotted lines to make it very clearly different from the incident wave fronts. You do need to draw the arrow on the line to show the direction in which the waves are traveling. Draw the line until it touches the reflector. Now, if the diagram you're given already has the directional arrow, you can skip this first step and go straight to the second step, which is to draw the normal line where the directional arrow touches the reflector. So what is a normal line? A normal line is a line that is perpendicular to the reflector. So at the point where the arrow has touched the reflector, that's where you draw the normal line. Next, you need to draw the directional arrow to indicate how the waves are reflected, where the angles are equal on both sides. Remember that the angle of incidence and angle of reflection are measured from the normal line. So as you can see, I've labeled here, this is I, which is the incident angle, and this is R, which is the reflected angle. Both angles must be equal. You should be using a protractor in this case to make sure that the angles are equal on both sides. Now we need to get the directional arrow first before we can draw the wave fronts. Now you need to have this line because you need to get the angles first before we draw the wave fronts. And now that we have the reflected direction, we can now draw the reflected wave fronts. So remember that the wave fronts are perpendicular to the direction of travel. So this is how we can draw the reflected waves. So the reflected waves are perpendicular to the direction of travel, and we have to make sure that the wavelengths before and after are equal. So when drawing the reflected waves, make sure that the angles of incidence and reflection are equal, the wavelength before and after reflection are equal, and the length of these wave fronts before and after reflection are also equal. Remember that when it comes to reflection, the only property that changes is the amplitude. And you can't see the amplitude from the top view. So everything about the reflected waves should look almost identical to the incident waves. The only difference is the direction in which they are traveling. Now, let's go briefly into the applications of wave reflection. So one of the common applications of wave reflection is an ultrasound, which is used to look at the image of the fetus in a mother's womb, or sometimes used to observe organs inside a patient's body. Radar and sonar are also applications of wave reflection. They all do use slightly different waves, where ultrasound and sonar uses high-frequency sound waves, whereas radar uses microwaves. However, in all of these cases, the method in which wave reflection is used are the same. Basically, all of these are used to detect an object in terms of the distance they are. That means how far they are from the point of reference. So how is wave reflection used to determine the distance of these objects? So here, I'm just going to explain very generally how the wave reflection is used. So let's say this is the transmitter and receiver of the wave, and this line here represents where the transmitter and receiver are placed. So for example, if we were doing an ultrasound, this would be the skin of the mother or the patient. Whereas if it's for sonar, this is the surface of the sea. Of course, for radar, there's no boundary, but the transmitter and receiver are in a fixed position. Let's say this red blob here represents the object to be detected. For example, the fetus or the fish or the airplane or anything else that we are looking for. So what happens here is that the transmitter will transmit a wave, and the wave will be reflected off the object to be detected and will be picked up by the receiver. So that's why the transmitter and receiver are normally in the same device. That means they have to be at equal positions from the object. So the main thing here is that we want to determine how far away the object is from the transmitter and receiver. That means we're looking for the depth of the object, which I have labeled here as d. Now, in order to determine the depth, we must have the speed of the wave. And yes, we have that information. The speed of the wave will always be the same in the same medium. For example, for ultrasound, the speed of sound will always be the same in the patient's body. Same thing as sonar, the speed of sound will always be the same in water. And for radar, the speed of microwaves will always be the same in air. Now, to clarify, I'm not saying that all of them have the same speed. I mean that the speed is constant for the respective wave in the respective media. So because we know the speed of the waves, we use the basic speed formula, which is speed equals distance divided by time. So we know the speed, but we're looking for the distance. What the transmitter and receiver will be doing is to measure the time it takes for the wave to be transmitted and to be reflected back. That means that this device will measure the time difference between the wave being transmitted and the reflected wave being received by the receiver. So when we know the time it takes for the sound to be reflected back, we can calculate the depth this way. Modifying the formula, so we get distance equals speed times time. But if you observe how the wave travels, the distance is actually double the depth because the wave has traveled down and back up. So distance in this formula is actually 2 times that of depth. So the distance in this formula here is actually double of the depth. So taking this and substituting it into this formula, we get 2 times depth equals speed times time. So to get the depth, meaning how far the object is away from the transmitter and receiver, we just need to take speed times time divided by 2. And this is the formula that is used to determine how far the object is away from the transmitter and receiver. And that's how all those devices use wave reflection to determine how far away the object is. Now, if you'd like to see some examples on how to use this formula to solve problems, do check out my video about calculations involving sound waves. I will put the link in the description below. And that is it for this video. So, if you found this video to be educational and helpful, please click like and comment letting me know how you have found this video to be helpful. If you'd like to help me keep making free educational video lessons and lab practicals, donations are welcomed at my Ko-fi page. That's ko-fi.com/physicsrocks. Do check out my YouTube channel for videos on other topics which you might find helpful. If you'd like notes, quizzes, and syllabus updates, do check out my website at physicsrocks.com. Subscribe to my YouTube channel for more free physics lessons from your physics teacher, Miss Ho. Happy studying!